Well, good afternoon, everybody. Welcome to the MTL Seminar. As you may see, this term we have the great fortune that MIT Nano allows us to use this space to hold the seminar. We're very grateful for that. And today, we have our first speaker of the fall schedule, Professor Clark Nguyen from Berkeley University. I happen to know Clark, be a colleague and a friend in the field of MEMS, but he's far more than that. He was a DARPA manager for a while, and you were a star. That's how I actually met you, doing mass spectrometry, portable mass spectrometry. And he's also the co-director of BSAC, which is the equivalent for MIT Nano these days at Berkeley. Thank you so much for coming. You are given the first seminar on MIT Nano ever. It's a great honor to have you here. So without further delay, let's thank the speaker, and the stage is yours.
Okay. All right, so thanks very much, Louis. It's great to be here at MIT, especially in this building for the first time for me. And it was a joy to be reminded that Dennis Grimard actually is putting a lot of this stuff together. I worked with Dennis for a while at the University of Michigan, and I can understand why you stole him from Michigan, because my God, the guy's good. And so what I'm going to talk about today is, I guess, crazy stuff. And that's what's fun about going to universities and giving talks here. I don't have to talk about the most practical parts of my research. I could talk about some of the more blue sky stuff. And blue sky is all mechanical microscale radios. And so I'll build up to this here in this talk, and so this is my outline. The first thing I'll talk about is the advantage of using MEMS in RF right now for radios. And one of the big advantages is the selectivity. The frequency selectivity of MEMS is so high that you can actually do something called RF channel selection, which means you grab the channel at the front end, not just the band. And in order to impart why that's an important capability, I'm going to review a little bit some of the bottlenecks on current wireless communications capability, and then focus in on the benefits of that high mechanical Q and what it can do. And then we'll talk about how you can use MEMS specifically to harness these types of advantages. And one way to use MEMS, it's kind of like transistors. You can use a lot of them. So if you can learn to build big circuits out of MEMS, then you can make things like micromechanical filters and go to maybe something that can reach LSI MEMS, so large-scale integrated MEMS, just like large-scale integrated circuits. And that would then create something like this micromechanical filter. But it turns out that if you really want to consume very little power, you can do something even simpler and maybe look at something like a MEMS-based super regenerative receiver. So this is the next thing I'll talk about that only uses one MEMS device together with transistors to create a receiver that consumes very little power. And that, in the end, is one of the big advantages of this technology. It can lower the power consumption of communications enormously. And so what would be the best way to reduce power consumption? Well, it would be to not have any DC power at all. And that's what an all-mechanical receiver might be able to do. And so we've actually demonstrated now all-mechanical receivers that really consume no power while listening. They do have to consume power while processing bits, while actually receiving bits, but they can listen without consuming power. And that's a big thing for future generations of IoT. And so with that, I'll conclude in ways that going to really low power can actually change the way that we view society and how we do different things in it. So again, let's start out with a little bit of review here on why there is a MEMS advantage. And again, that's RF channel selection. So here, I'm going to take some kind of wireless phone. And so I use a comic version of a smartphone so as not to favor any of the companies we work with in that sort. But the innards of this phone, you know, consist of a few things. One, you're going to have an antenna that's going to pick up that electromagnetic energy. Then you're going to have a bunch of transistor circuits that will do demodulation of that energy in many different ways, depending on the type of standard that you're using. Now, in general, you don't do this entirely with transistors here, actually, although some can do that. You have something on this that serves as a reference, so a timing reference, and that's usually a quartz crystal oscillator. And so this delves into the practical side of MEMS. So a lot of what I've done in my early career has been attempting to replace quartz crystal oscillators. And so now what we're seeing is MEMS doing that. And so MEMS technologies, as pursued by Dacera, which was my company that started a lot of this. It was the first company to try to commercialize MEMS technology for timing. Now SciTime is the survivor, I suppose. I guess no one survived. We all got bought, which is a good way to survive, I suppose. But SciTime at least has kept their name right now. But what you're seeing now is that MEMS oscillators, compared to quartz, are actually better in terms of aging, temperature stability, et cetera. Quartz still has a huge market share, but the MEMS market share is getting bigger and bigger and bigger, and it's going to get better as people realize how good the MEMS performance is right now. But this is one aspect of a technology that can already go into a wireless communicator. What I want to talk about, though, is the specifics of what you have to do for wireless. So think of what your smartphone is doing. You're trying to pick up power at a very specific frequency. So maybe this orange signal is your desired signal. And you're trying to do that, have your conversation at the same time that a lot of other people are having simultaneous conversations. There could be some cell phones that are very close to you that are putting a lot of power out, and so this power is much higher than your power. And think of this as a dB scale. So every inch or every millimeter of increase in the vertical scale here is a lot of power increase there. You want to pick this up in the midst of all of this. And so you could try to do that with just your antenna and transistor electronics and maybe these oscillators here. But if you tried to do that, you would run into a problem in that your transistors are not perfectly linear. And if they're not perfectly linear, then what happens is that frequencies that were not in your band are now created because of interactions between these strong interferers and the nonlinearities in your system. And so this signal here that's generated here that wasn't there before can now mask the signal you're trying to pick up. And that then prevents you from actually doing your wireless communications. And so one way you could solve this is to try to make the transistors as linear as possible. One way to do that is to pump a lot of power in your transistors. Unfortunately, these are your smartphones or some kind of handheld device, and they're battery operated. They're not going to last long if you try to do that. So the solution that they use in today's wireless industry is they put a filter in front of all this. And so a popular filter being used is maybe an F-bar filter, is what you're looking at right here. That's a film bulk acoustic resonator technology. Broadcom used to be Avago. They're making gobs of money doing this. And so if you actually look at how much money Broadcom is making, a very large percentage of that is coming from these filters. They're MEMS technology. They're a vibrating filter here. And they're needed for all of these cell phones because what they do is if they have high enough Q, they can make the design of the demodulation electronics much simpler. So think of this as a whole system. I have these electronics. I have this filter in front of this. This filter decides how complex and how much power all of this consumes. So for example, in today's F-bar filters, which you can see are about 1.8 gigahertz, 2.4 gigahertz, et cetera, they presently use resonators with Qs on average about 1,500. And if you can have a Q that high, then what you can do is make a filter, a frequency filter, that maybe has this transfer function. So it passes these frequencies, and it rejects all those frequencies that were causing problems there. So now suddenly you get rid of that interference problem. You can lower the power consumption of the electronics. They can be a little more nonlinear. And so now suddenly your phone can last, what, a day or two on a charge. And you can ask yourself whether you're happy with that. Okay? If you're not happy with that and you'd like your phone to last longer on a charge, then one thing you can do is try to increase the Qs of these resonators. So if you can increase the Qs of these resonators, and that's what many people have been trying to pursue in the MEMS community, at least in the RF MEMS community right now. So you can see a number of names here that I'm showing, Gianluca Piazza, Donna Weinstein. A lot of these people here are trying to make resonators for different purposes, but a number of them trying to get as high a Q as possible at as high a frequency as possible so that they could take this filter spectrum here and instead of have this wideband here, make it even sharper. Because if you look at this, there's my signal. I still have other signals in here that can combine to create a nonlinear image on top of the desired signal still. Right? So that's what forces me to consume a certain amount of power in this electronics here. If I can make that filter small enough to be like this, which would require Qs greater than 30,000 at these gigahertz frequencies, then I can knock out all of those interferers. Suddenly, I don't have this nonlinearity problem anymore, and I can relax the specs on all of these electronics to the point where that power consumption plummets. Okay, so that's one of the far-reaching goals of a lot of this RF MEMS type research, to try to do something like this. And so the question is, how do you get a resonator that has a Q that high? Well, this is an example of one of them right here. What this is a ring constructed in a diamond material. So this is a deposited diamond material. And the structure is shown here. So it's diamond, sort of diamond-like carbon, so it looks black in this SCM versus the polysilicon electrodes around it. But what you have is this ring structure here, and this is the mode shape that it takes. It's sort of a breathing mode shape, where it expands and contracts along its outsides. And it's held in the center, which is a great way to hold it, because if there's any forces applied on this, they are all equal in balance, so they cancel at that center point there. That means you get less energy loss to the substrate there. And that allows this resonator to have an extremely high quality factor. So you can see here that at a frequency of 900 megahertz, which is a popular cell phone type frequency, you have a Q of 77,000, which is plenty to do that RF channel selection that I was talking about. Okay, the problem with this is this resistance. Okay, and that's been the problem that people have been fighting in this community for a while. In order to, for example, match to antenna, you need this resistance to be on the order of 50 ohms. Okay, that's only because 50 ohms is the convention. You can actually make that resistance anything you want in a real system. But this is way higher than 50 ohms, and probably way higher than the 200 ohms or 500 ohms you might choose if you didn't choose 50 ohms. Okay, so how do you solve this problem here? This has to do with the transducer, and I'll talk about this in a second. But there it is. You have the Q at least, and you just have to solve this resistance problem. And so once you create a resonator like that, if you have a good enough resonator, and so now these are different types of resonators. That was a ring resonator. This is now a disc resonator that has a mode shape like this, where it's still expanding and contracting around its circumference here, a breathing mode shape here. But you can now take these resonators and you can make big circuits out of them. And when you make big circuits out of them, that's one solution to this impedance problem. The other thing you can do with these big circuits is sort of shape your response, so it's not just some sharp bandpass biquad, but you actually have a flat passband response. You have a sharper roll-off to the stop band. So now this is 50 dB of stop band rejection. Very small percent bandwidth, exactly what you need to select a channel there. And with that, very little insertion loss. You could not do this with a technology that has a low quality factor. You have to have these high Qs, and in this case, the Qs were over 8,000, at least for these types of resonators. Okay, so this is a lot to look at right now. I'm going to take some time to sort of dissect what this circuit is a little later on, but I'm just flashing this at you right now. In fact, not a little later on, right now, I'll do it. So let's talk about this channel selecting micromechanical filter and how we construct it. So first of all, let's talk about the base resonator being used in this. And so this is it. Okay, so it's basically a disc. It's suspended in the center like, with a stem, like a mushroom. And it's surrounded by these electrodes. And the gaps between the disc and the electrode decide how strong that electromechanical coupling is. So in the old days, we used 100 nanometer gaps. Nowadays, we're down at 10. And there's a huge difference between 10 and 100. 100 is at 50 kilo ohms. 10 is now 25 ohms, or thereabouts. Okay, so we've now taken that resistance, and it's plummeted now from what it used to be there. And so the frequency of this device, which is a very important thing, it's, for any mechanical device, is a ratio between stiffness and mass, so the square root of that ratio. So you want to increase your stiffness as much as possible, lower your mass as much as possible. And in that case, it tells you that you can get to high frequency if you can just make that mass as small as possible. Okay, so that's exactly what MEMS technology is trying to do, to get to these frequencies. Now, if you expand this, you see that this is, of course, a function of material properties like Young's modulus and density. So this ratio of Young's modulus to density under the square root, that's an acoustic velocity. So that decides how fast the waves move in the mechanical material. And then finally, the radius of this device determines that ultimate frequency. And so that's a nice thing about this device, because what it tells you, unlike an F-bar where the frequency is dependent on thickness, the frequency of this device is dependent on a lateral dimension, which is CAD definable, which means you can make all sorts of different frequencies on a single chip. That's something you cannot do with the F-bar technology that I just talked about. That's making gobs of money. So if you can make this work, think of what you can do. Take all the filters in your cell phone, which now there's, what, 20, 30, maybe there's a lot of filters in your cell phone now because you got all these LTE bands. Okay? put all those into a single chip that you can now pay 10 cents for to make, but still charge, you know, the $5 or make it 1 cent cheaper than all those other filters there. And that would be a great business, actually. But, you know, we're not there yet. There's a lot that has to be solved, and so we'll talk about that. So the way that you operate this device, the way you get it to move that way is you put a voltage on the device. You're really just putting charge on it because there's no current path here. So there is no DC current flowing, no power consumption. Okay, then you put an AC signal, and this could be your RF signal. That would then drive this with a force that's proportional to this bias voltage in that AC signal to make it move at its resonance like this. And what you really have is a time-varying capacitor across which you put a voltage. And so if you have this situation, then you'll get a current. Usually your current across a capacitor, if you're an electrical engineer, is C times dV/dt. In this case, it's V times dC/dt. Same kind of current coming out of this thing. And if you take an actual device like this, so this one is made in diamond material here. There's the disc with the stem. These are the electrodes around it with very small gaps that you can't really see. You could then trace out a very high Q spectrum. So in this case, it's 11,000 in vacuum at 1.5 gigahertz, 10,000 in air. So a big thing about this technology in the past was that you had to be in vacuum to get these high Qs, no longer at high frequencies. And a lot of this has to do with the fact that now you've got a lot more energy in this resonator at high frequencies. The stiffness is so high, the energy just to push around gas molecules is enough that you don't lose your quality factor as much as the lower frequency resonators did in the past. Okay, so this is our device here. And the nice thing about this as well is I can turn this resonator, an eventual filter, on and off at will. So it's kind of like an LCR tank circuit, but if I make the bias voltage on the device 0, I'll get no current out, which effectively means I've shut it off. It's almost like a transistor, LCR, and one device. It's a very nice device to be able to play with at the front end of a communication system. So I showed that poor resistance with that other resonator there. Here's one of these disc resonators. This one now has a gap spacing of 13 nanometers. Okay, and so that's an SEM trying to show you the gap spacing. There's no way you can know whether that's really the gap spacing or not. And we actually can't measure that except by measuring the frequency shift with DC bias, which occurs because of electrical stiffness across this device. And so I'm not going to explain that electrical stiffness concept in great detail here, but just suffice it to say that the frequency of the device can be tuned by voltage, and the amount of tunability you get will tell you how small your gap is. And so just from this plot here, we're able to see that the gap, in this case, is 13 nanometers. And with 13 nanometers for this device, you can see the motional resistance is down at 54 ohms. Okay? And so making that gap smaller allows us to get to impedances now without piezoelectrics. This is all capacitive transduction, so electrostatic transduction down to 50 ohms. And so this now suddenly becomes very practical with these small gaps. And so let's move on to talk about, so that's a device. Let's now build the filter. So to build the filter, what do we want? So we start with this disc resonator. And this disc resonator alone has this bandpass biquad transfer function. Very sharp spectrum, very high Q. What we want for a filter in a comm system, though, looks more like this. We want a flatter pass band. We want a sharper roll-off to the stop band. Maybe we even want a loss pole there that can knock out some particularly troublesome interferer. Okay, so how do you go about creating this transfer function? Well, you make a circuit out of this. The same thing you do in electronics, you do in mechanics. Except you make the circuit out of these mechanical disc resonators, and you link them together mechanically, not electrically. Okay, so you're really linking the velocity in this case to the velocity of that to the velocity of that, transmitting them down these mechanical lines. This is great because now you are immune to parasitic capacitance and other electronics going to the substrate. So you basically convert everything to the mechanical domain here. You process in the mechanical domain, and then you reconvert to electrical if you have electrical stages after this. You'll see later on, I'm not even going to have electrical stages after this. This is going to be all mechanical. It'll be a much simpler mechanical circuit. But anyway, this is your filter. What you're really doing here is you're creating a multi-mode mechanical system. So with 3 resonators coupled this way, I now have 3 modes of vibration. And if I select the lateral dimensions of this, which I could do by CAD layout appropriately, I can put those modes exactly where I need them to be to form this eventual filter. This is what we're doing when we create LC filters, when we create microwave filters. There's not much different here from that. This is just doing it mechanically, where the mechanical advantage is you have much higher Q, and everything can be much smaller. because the acoustic wavelength at the same frequency is a lot smaller than the electromagnetic wavelength. Okay? You then can, like any filter, you have to terminate this with the right impedance, so the right resistive termination in this case, or quasi-resistance there. And what that does is it flattens your passband to get that filter. And if you want that loss pole, what you do is the same thing you do in circuits. Instead of interconnecting adjacent resonators, which I've done right here, you just interconnect non-adjacent resonators in the right way. It's all designable, and you can bring that loss pole in there. You can put two loss poles, as many loss poles as you want, depending on how big your filter is. Okay, so this is how you design a mechanical filter. People do this already almost with F-bars, except they're not all mechanical. In F-bars, you use several resonators, and you're sort of coupling them together with capacitive couplers. Okay? So what's really new about what people have been trying to do is they're trying to learn from the IC revolution. Okay, so what did we do with integrated circuit transistors? What spurred that revolution? Well, we had massive numbers of tiny devices. We had the ability to design circuits hierarchically. So you have the simple single device, you create some sub-circuit of that, and then you create your larger circuit with many of those. Continuous technology advantages brought about by scaling. Okay, so with this, right, this is integrated circuit CMOS transistors here. You know that this is a small signal circuit. If you're trying to make an analog circuit like this here, all these tricks that we have here, right? We can do differential design, replica design. We generate references, current references off of this, doing mirroring and have control voltages for feedback and for other inputs to set the bias of this thing. We have all these techniques to build this transistor circuit. We can do the same thing mechanically. It's all exactly the same stuff. And so in this case, maybe you can argue high gain for transistor permits you to cascade a number of devices to make a circuit like this. But in the mechanical integrated circuit world, think of what you have. You've got massive numbers of tiny devices. I'm going to show that you can do hierarchical circuit design. You've got continuous technology advantages brought about by scaling. Again, that resistance change happened because we just scaled that gap there. And if you want to go up in frequencies, you just continue to scale the sizes of things smaller and smaller. So the equivalent circuit for this is that. Okay? It's a little different than the transistor equivalent circuit, but so what? It's a circuit. We can use that. We can create CAD programs to create a structure like you see to the right, where this represents each individual device there, and they're all identical in this. And we can do things like energy summing here to lower that motional resistance and increase our power handling capability. Energy mirroring, which is what this quarter wavelength is doing between these structures here. Feedback in the form of actual electrical resistors there to knock the Q down a bit, and then control inputs on this as well. So you've got a lot of circuit design capability just in the mechanics right here. And so let's build this circuit here. Let's see what we did to create that filter. And in this case, for mechanics, you could say that you don't have gain in the mechanical elements, but you do have high Q, which means you have very low loss, which then allows you to cascade many elements to create a big circuit. So whereas in integrated circuit transistors, you put power in to create gain so that you don't lose your signal as you go across the circuit, in mechanics, you don't have to put power in. You have such low loss that signal stays there across the whole thing. So it's an ideal technology to get very low power implementation. So let's now design that whole filter there. And so again, we start with this single disc resonator, and it has this single bandpass biquad spectrum. Okay, so what are we going to do? This is too high a resistance. So there's not enough current coming out of this. So what we do is we take this single resonator and we now couple it, appropriately coupling it. These are half wavelength coupling beams. And if you couple with half wavelength coupling beams, what that does is it forces all of these resonators coupled together to go at exactly the same frequency at the same mode. That allows you to add all of their currents together. Exactly. Okay, so it's a very convenient thing to be able to have. And so that current goes up. That lowers your motional resistance right on the spot there. Okay, now to make that filter, we're going to do the same thing that we showed before, which is take another one of these resonators. So take now another one of this, I would call this the second level of hierarchy, which is this array. Couple that with another array using lambda over 4 beams. And so the lambda over 4 beams basically equates the energy on both sides of this. And it actually splits your frequencies to create that filter response. Okay? And so you end up with this filter response, but there's still a problem with this. You got enough current coming out of this, but you don't have enough rejection. And the reason why you don't have enough rejection is because you got feed through from this end to that, going through the substrate, over the thing, maybe through the thing. And so one way to correct for feed through is use differential design. So you actually create another mirrored version of this below this, now couple with a full lambda beam. And if you couple with a full lambda beam, what that does is it forces this array to vibrate exactly 180 degrees phase shifted from this array up here. Okay? So all these tricks that we're using to allow differential design here, and that now makes the parasitic feed through plummet. And so suddenly you get this filter that has, very good rejection in the stop band. So this is how we get to this. Right? This is exactly that structure. You can see that it's very much strategic circuit design, hierarchical circuit design to create this thing to finally give you this performance, which I would say is the best performance of any of these filters to date at this frequency, which is not in gigahertz. This is at 224 megahertz here, but still usable at gigahertz frequencies as well. Okay, and so just to bring home the importance of this circuit design, if I didn't make this differential, the story would be completely different here. And so here's the proof of the pudding. If I just made a single-ended part of this, so just the top half there, without the differential, this is what we measure. It's a horrible filter. And so not only do you get this parasitic feed-through coming through, you also get all these modes sticking in there. And so one thing that balanced differential design, and I think this is universal across any circuit design that you get, if you can balance the thing, do it. Make it symmetrical. Because this symmetry not only gives us all this, but it takes those spurious responses and sticks them all the way down. And if you're an F-bar designer for Broadcom, who again are making gobs of money doing this stuff, the secret in the pudding is not necessarily the technology. The secret is how to get rid of those spurious modes. That's why they're able to sell so much. That's why they can lock other people out of this game, because they have a formula for killing off spurious modes. That's why you see, if you've seen an F-bar filter, they have these polygonal shapes. Those shapes are there to knock out the spurious modes. And that's what all the competitors are trying to do. They're trying to kill the spurious modes. Well, this kills the spurious modes just through balancing. Okay, very nicely here. So it's a nice filter technology. And on top of that, it is a channel select filter technology that you can get because our Qs are so high in this technology. All right, so going back to this. So we have this technology now. We don't have it at the gigahertz frequencies yet. So there's still work to be done to do that. But if we get that, this can work for a sort of VHF type of communication capability as well. But if we get that sort of thing, now we could take this whole thing and instead of having maybe a single filter, maybe have several filters or tune them over a certain range. So I should say these are not widely tunable. The higher the Q of your technology, the lower your tuning range usually, although that's starting to change. So at upcoming conferences, you'll see both high Q and large tuning range. But at least if you can't tune, what you'll do is you'll just build many filters and just tune that channel across whatever range that you need it to be. And if you can do something like this, then I already told you you can simplify these electronics here to lower the power consumption to make this a lot more linear. But the other thing you can do is just completely change what you're using as your communication front end. So instead of going to that complex circuit, demodulation circuit that everyone uses today, that was sort of a zero IF type conversion system there, or direct conversion system actually. This is now something much simpler. This is a super regenerative circuit. It uses very few circuits. These circuits consume very little power, and it's able to do that. It's a highly nonlinear gain function at the front end. And we're able to use that highly nonlinear gain function because we've now got that RF channel selection here. Okay, so let's see how this thing works here. And let's talk about this, the MEMS-based tunable super regenerative receivers. This is actually something that started a new company now to try to put out MEMS-based receivers for very low power applications where the receiver has to stay on at all times. And what is this? So first, super regeneration. So a lot of people here probably know what this is here, but I guess I'm going to explain it for those that might not. So this is a technique invented by the same person that invented most of the radio concepts that we have, like the super heterodynes. That was Edwin Armstrong. So he invented super heterodyne radio architecture, frequency modulation. He also invented super regeneration. Okay? And there are tales that say he likes super regeneration more than his other inventions. I don't know how true that stuff is, but I've heard those tales there. But this is a technique to amplify weak signals using very simple circuits. And so one way to amplify this signal Sn is just have just gobs of amplification here, power amplification to get to the other side. The other way to do it is to have a much smaller amplifier and let this signal go through this, then take it back and let it go through again and again and again. And then you keep multiplying the gains of that amplifier. There are obvious problems with noise and that sort of thing, but this is one way to try to do amplification, and this is the super regeneration concept. So the way that you would implement this, I mean, this is just an oscillator is all this is. Okay, so you would take a frequency selective tank like our mechanical resonator or an LC tank of some sort, embed it in a positive feedback loop with a sustaining amplifier like you're seeing here, and that creates an oscillator. But the interesting thing about this super regenerative concept here is you're now harnessing the fact that this oscillator becomes steady state oscillation with different amounts of startup time. And so if I just start with noise and I have nothing else in this circuit, and that's how all oscillators start, right? They're really just noise that's been filtered in such a small bandwidth that suddenly it becomes a more deterministic signal with a longer time constant there. But if you just start it from noise, it's going to take a certain amount of time. However, if you're able to inject energy into the loop in some way, maybe wirelessly, say you hook up an antenna, you get RF energy coming in. If it's the right frequency, that now allows you to start up much faster, and you'll reach a threshold much faster. Okay, so this is a difference then between a 0 and a 1. Right? If you're doing digital communications, this is how you represent your 0 and 1 in this case. So you can now try to use this to do communications. And so I'm about to show this, but what I'm about to show is going to use this device here that now has 4 electrodes around it. It actually has a mode shape that looks like this, so it sort of expands and contracts along orthogonal axes. And 2 of these electrodes I'm going to use for filtering. 2 of these electrodes I'm going to put in a positive feedback loop to create an oscillator. But before doing that, let me just mention a few things about this technology and why it made so much sense for oscillators. So why do these companies do so well with the oscillators? So first of all, this is at 61 megahertz. Look at the Q, 145,000. Some of these have been measured over 200,000. This is in polysilicon technology. And the support structure you use to support this will dictate how much Q you have there. But in this table here is the comparison I want to make. So here's 13 megahertz quartz, what's been used for timing and frequency references for a very long time. Its Qs can be on the order of 10,000. It's Cx over C naught, which is the same as KT squared. I like to use Cx over C naught because it's more of a circuit design concept there. But they're the same thing. It's on the order of 0.43%. But its capacitance is on the order of 7 picofarads usually across that quartz crystal. That's a lot compared to MEMS. So if you look at MEMS, a 10 megahertz clamp beam, so a beam resonator, they might have a Q of 8,000. Its capacitance, shunt capacitance, 7 femtofarads, and much higher Cx over C naught at this 10 megahertz frequency. And then at 61 megahertz for this device, 150,000 Q, still a very small C naught, and comparable Cx over C naught to quartz. Okay, so what does this tell me? This tells me the big advantage is in this C naught. And if you do oscillator design, you'll know that that C naught makes a huge difference. That C naught is this capacitor between the electrodes around the device. So for quartz on this side, that's 7 picofarads. And if you're designing a Pierce oscillator, if you have 7 picofarads across the gate to drain of your drive transistor here, you need to hang some large shunt capacitors here to compensate for that so that you retain the gain to actually get oscillation. And so those capacitors for quartz typically are 20 picofarads out here. Well, to drive 20 picofarads takes a lot of energy, and that's why your quartz crystal oscillators are usually consuming milliwatts in order to get certain phase noise performances or jitter performances that we need in a lot of our modern systems. Okay, go to the MEMS side here. Same type of resonator, even higher Q than quartz, but now the capacitance across these electrodes on the order of 5 femtofarads. That means I can use 10 femtofarad shunt capacitors here. That means the power consumption required to get the same performance plummets. It goes down to microwatts of power. Okay, so there's the big MEMS advantage for oscillators. One of the MEMS advantages. The other MEMS advantages are they're actually more stable because of the way they're manufactured, at least by side time, is so clean that their aging rate is better than quartz now. And in addition, they actually can get the thermal stability better than quartz. So everything with MEMS now is better than quartz. It's just a technology that's taking time to gain market share, but they are gaining market. You all have MEMS on you right now, if you have a cell phone, if you have any Apple products and that sort of thing, and these MEMS types of oscillators here. But we want to use this oscillator now for a communication device. So this is our super regenerative receiver. And so this is a lot to look at here. You can see the MEMS resonator embedded in some circuits here. This is a lot to look at right now, so let's do this piecemeal here. Okay, so what I'm showing here is a situation where this is actually a demonstration of wireless reception. Okay, this is your transmitter here, and we're doing exactly what we need. We're creating a bit stream that we want to transmit, and we're modulating this onto a carrier, so we're basically making an FSK signal here. Putting that on an antenna with an amplifier, then transmitting that to another antenna on the other side. So these these are the zeros and ones. Of course, this is an instantaneous thing. It's really going to look like a spread of frequencies across this. That's reached by another antenna, which goes through a balun into two of the electrodes of this wine glass disc device that I showed. Now, between those two electrodes, that's the filtering electrodes. These two electrodes, then, I'm going to put into a closed-loop feedback system that will then sustain oscillation, or at least will start up oscillation for me. And so what this circuit is doing is it's first filtering the signals coming in. So there's my channel selection. I'm grabbing the ones, not grabbing the zeros. Okay, I need to grab the zeros to get full FSK, so what I'm going to show is really OOK in this case, on-off shift keying. But I'm grabbing this one here, and if I get a one, then this oscillator is going to start up very quickly. And so what I'm doing is I'm quenching this oscillator every cycle. So I quench it, then I turn it on again, I let it grow, then I quench it, it grows, etc. And every time it grows, if it takes a long time to grow, it's a 0. If it takes a short time to grow, it's a 1. Right? The 1 tells me someone's transmitted energy that's made it through the filter because it was at the right frequency. Okay, then at this point here, we then do an envelope detector to get the envelope of this, use a comparator to tell us whether we've reached this threshold fast enough or not. And if we have, it's a 1. If not, it's a 0. Okay, then there's a flip-flop here to really buffer that output. And hopefully this at the output is the same as the original transmitted signal. Okay, so we hooked this whole thing up, did it with wire bonding. So here's the device. It was wire bonded. You can see the two chips to an on-chip ASIC sustaining amplifier here. This is now in a vacuum bulb. This is all university stuff, right? We don't have all the packaging technology to do here. But here's that vacuum bulb with a receive antenna here. It's a whip antenna. This is 60 megahertz. And so you've got another antenna on this port. So it's pretty much across our lab that we're actually demonstrating this communication. And this is the result here. And so this actually is the bit stream that we modulate then and transmit. That's received at the other end and envelope detected. So you can see the envelope detected inputs there that are crossing the threshold that then comes to create the output of our comparator. And after the flip-flop here, you can see that the bit stream coming in after going through this wireless channel is exactly the same as that coming out of this. So it has successfully received and demodulated this signal, recovering the information we started with. And it did this with a sensitivity of minus 90 dBm, okay, which is not bad. The antenna actually was not matched to the device because this device didn't have small enough gaps. So if it were matched, this could have been minus 102 dBm. That's now getting on the order of cell phone type sensitivities. And the power consumption, with decoding OOK data, with 16 microwatts transmitted power here over 5 meters, was 490 microwatts initially, but when we started correcting for the capacitance in the oscillator, this is now down to 30 microwatts. And so that's the continuous received power that this has, basically doing OOK, maybe double the, probably not even double the power for FSK. A little more power for FSK, but you know FSK is what's being used in Bluetooth and that sort of thing. This is not at the data rate of Bluetooth, so it's a much lower data rate than that. But it is very useful for low data rate things like IoT because the power consumption is so low. And so these are the tricks that you can play with MEMS right now. And the reason why we're able to do this, let's bring it all the way back to the front. We've got that RF channel selection at the front that allows us to use a very nonlinear receive circuit that then allows us to take the power all the way down. Okay, so the whole concept, the whole system is working at least in this simplified circuit here. But what if you wanted even less power than this, right? This is already very low power versus most of the things that are out there. And again, there's a company started based on just that concept there. What if you wanted even lower power? And why would you even want this lower power? Well, we're all talking about IoT, or people will call it a trillion sensor network. This is something that these ideas have been around for a long time. So this is actually a picture that I use in one of my DARPA slides to try to sell some of these types of programs or so. You'd fly a plane over some rough terrain here. You drop down sensors. Each of them would have a CPU, a sensor, some kind of energy source on this. And if you look at the energy of these things, and they would self-form, yeah, there they go. So they would self-form their own network. This would all be wireless here. And what you find in these sensors here, that the sensors in the CPU, they don't take that much power because usually the sensors aren't on for very much. Right? They wake up in that sort. What's taking most of the power is the transmit and receive in the radio. So you need to knock that power down. And so if we're talking about these, some predict that you're not going to have a trillion of these sensors, right? They want to take these walls and fill them with sensors. I don't know if you want that or not, or any of us want that, but this is what people would like to be able to do. And if I have a sensor up at the ceiling there, I don't want to go up and change its power source, right? So power is premium in this case. And it's difficult to change these batteries. We want to minimize power consumption. And a conventional battery might be cost prohibitive. So the solution here usually is to put the radio on a sleep-wake cycle. That's how they solve the problem right now. But in that case, now suddenly your power problem goes from the actual system to your clock. Okay? Because in order to synchronize this, you have to have a clock. And most of these real-time clocks are consuming on the order of 1 microwatt of power. It may seem like very little power, but say you have this application right here. And let's take a look at how much power that really is. So if you could take a CR2032 lithium coin cell, you can buy these in a store, right? That's 1.4 kilojoules of power. At 12 milliwatts, that'll last 1.3 days, which is the power consumption, if I go back, of this transmitter. Okay, so you got 1.3 days out of it. If you can sleep this and just have effectively the power of the clock, then that's 1 microwatt. That would last 45 years. Okay, so that works. Okay, so what's the problem? The problem is, go to the store and buy this thing and see how much it costs and multiply that by a trillion. Right? If this is over $1, that's $1 trillion or more. Right? This is a big problem here. So you can't afford to use a lithium-ion coin cell for this type of application. You need to do something much smaller. Maybe an integrated battery is preferable with much smaller capacity. And maybe all you're going to get is 1 joule at the cost point that you want. So 1 joule at 1 microwatt, that lasts 11.5 days. You can do everything at 10 nanowatts, that's 3 years. Okay, so that's something decent now. So this is the type of power level we'd like to get to, even in the comms here. So obviously we'd like to consume 0 power, if that's even possible, especially while listening. And we'd like to do something like an RFID tag, right? These things that consume no power, passive RFID tags, they exist already. But the problem with these things, if you're trying to find if there's an issue with a pipe under this, you've got to take a wand and get really close to it with a lot of power coming out of that wand. It's tough to do something like this, where maybe you have a bunch of pipes going under this road, and you want to, from a distance, be able to just take a snapshot of that whole thing to find out where the problem is. Okay? And so the solution we've come up with for this, 0 power listening, is an all-mechanical receiver. Okay? So there's no electronics at the front end of this receiver. And so let me go through the concept of how this works. So it is doing the same thing that any communication system is doing. You're trying to take a bit stream. You're going to modulate that onto a carrier. You're going to send it through a channel. That's going to be received by this, which is our radio, well, at least our receiver right here. And hopefully the bit stream coming out will be exactly the same as the input bit stream. Okay, so let's do that. Let's take this bit stream, let's modulate it. Okay, so first let's represent the 0 with a frequency that's outside of the passband of this device. So this device is a simple comb-driven resonator, something that was invented a long, long time ago. The only difference between the comb-driven resonator, so these are the anchors right here, this is the supports, this is the shuttle that'll move back and forth as it vibrates. The only difference here is now this is designed to bang on an electrode. So it's going to make contact with an electrode. And when it makes contact, energy from this power supply is going to go to this electrode. Okay? Do I have to wrap up, or? I'm almost finished, actually. Okay. energy is going to come to this electrode here. And so if I'm outside of the frequency, nothing moves. And if I had any charge on this capacitor waiting here, that would go to 0. Okay, once I go into the passband of this thing starts moving. It's supposed to continue to move. It seems like a computer doesn't want to allow it, but you could still see the explosions as it hits that electrode there. But what's happening now is it is bumping that electrode, and every time it bumps, it's putting charge on that electrode. And it charges it up then to a 1. Okay, and so that was a different frequency associated with a 1, and so on and so forth. I go back to a 0, this stops impacting, charge comes off of this electrode there, and you pretty much repeat the bit stream that you get right at your output. So we've successfully now, at least conceptually here, taken this wirelessly transmitted signal and demodulated it to recapture that information on the other side. And then from here, if you want to use this as a wake-up detector or something, you can put these into a shift register until it matches the correct code that tells a sensor to wake up or something like that. Or you can do all sorts of different things with this, right? This is a digital circuit that I'm showing, which doesn't consume a lot of power, but this could easily be all mechanical too, right? So the whole thing could be mechanical to actually capture certain amounts of data here. And so does this actually work? Well, the devices we used to do this were fabricated as follows. So it's very simple fabrication specs. So we put down oxide, put down a chrome gold chrome, then more oxide on that. We would etch the oxide to form a mold, and then electroplate gold above this. This is just one fashion of fabricating this here. And then we get rid of that oxide, we get rid of that gold down there, we etch underneath with a timed etch so that our anchors stay around, and we finally end up with structures like this. So this is an all-gold version of this, I'd say, we call it a resonant switch. We abbreviate it as reso switch or so, but that's the main element then that's being used in this mechanical detector. And so does this work? I guess I've got a couple things. Yes, it does. Okay, so this is the actual demonstration of this here. So this is the device here. This is the circuit that we put it into. It's not receiving energy from an antenna right now, but it does respond to minus 60 dBm. In this case, it's a 20 kilohertz carrier. We've done it at 60 kilohertz, 80 kilohertz or so. But here's the input bit stream. This is what you get on the capacitor that this is impacting at the output. So you can see it goes to 1, falls off to 0, and that sort of thing. If we have a flip-flop at the end of this, this will make this much better behaved, so you can see that the output bit stream is the same as our input bit stream here. So we are doing actual communications here, communications receiving. It's not wireless because we don't have it across the antennas right now, but it is driven by a function generator, a signal generator in this case, and it is taking that signal, demodulating it back, and recapturing that input data stream. So this works, and it's minus 60 dBm. That's not bad. That's not the minus 100 dBm that you want for cell phones, but for sensor networks, a lot of people think minus 70 dBm is enough. So this is close to what's needed, and this is consuming no power while listening. Okay? As soon as it receives a signal like this, then it starts consuming power. It's got to draw power off of that battery on this. But while listening, it's consuming no power at all. And so this is very low-frequency communications. Right? I'm talking 20 kilohertz, 60 kilohertz. What's that useful for? Well, that's already being used to transmit times across continent. So if you have one of these radio-controlled watches or radio-controlled clocks, what's really happening is you've got a base station in NIST in Colorado. These are gigantic antennas out there, and they're putting a lot of power out. But these are transmitting across continents. So getting all the way out to Boston out here is really using the waveguide between the ionosphere and the Earth to curve that electromagnetic energy so it doesn't escape the Earth here. And so it's able to get out here, and your little watch picks that signal up. And there's an atomic clock at NIST, so that you can actually get very close to atomic clock time on a radio-controlled watch because of this. So that's going out to a radio-controlled watch. Inside that radio-controlled watch, you've got a ferrite rod antenna, and that's good enough to pick up that signal. Okay, so that picks up the signal. You also have a receiver chip. A popular one is the CME 6005. That consumes about 100 to 500 microwatts. Okay, so if you have this radio-controlled watch, you don't want that on all the time. So this only turns on 1 minute per day, exactly at 1 a.m., because that's when there's the least amount of noise over the atmosphere. Okay, just think what you can do with this MEMS technology if you can replace this now with this Reso switch receiver, right? This is now, doesn't consume any power while listening, so you can have it on the whole day. I don't know if you can receive your signal the whole day. It depends on how noisy the environment is, but this now can be on the whole day. You can do communications anytime you want with this thing. On top of this, if you insist on still doing your sensor networks with a clock, okay, remember I told you the problem with a real-time clock is it consumes a microwatt of power. Okay, this thing can do the clocking consuming much less power if you make this a remote clock. So if you take this device and excite it now with a reference clock that could come from an atomic clock, well, you get this same sort of thing here, and you can then reproduce that reference clock, but now with only possibly picowatts of power. Okay, so you get a picowatt clock that has almost the accuracy of your reference clock, but unfortunately not the stability of your reference clock. So one of the issues with this, and so basically I'm showing you all the good stuff, right? You know that's what I'm doing. But there's all sorts of stuff behind the scenes that may not be working just as well. And so here's one of them. Okay, so one of them is what's really happening here. If I looked at the Allen deviation of the MEMS clock, which is the red, versus the reference clock down here, you can see it's much worse. Okay, that's telling you the stability is much worse. And why is that stability much worse? The accuracy could still be very good. And a lot of times that's what you need, but the stability is not there. And the reason for that is if you look at the signal here, as we're charging up that capacitor, yes, we charge it up, but we would like this thing to continue hitting continuously, like I'm showing right here. But what really happens is once you hit, what is that? That's the energy loss. And so you come back, and maybe you don't hit again. So maybe you come back just this far, and now you got to grow back to that amplitude and hit again. So it's a squagging type behavior. You see this in electronic oscillators where it comes up, it comes down, it comes up. So this is squagging a bit, and if it squags too much, then you can get a dip that's so low that that suddenly is interpreted as a 1. And you get that extra transition there, which then is interpreted as a frequency change. Okay, so you get less stability because of that. So getting this to work better is about removing that energy loss as we're hitting this thing. And so there's a lot of cool things to learn about this. You know, how do we do that? We've discovered a lot. So it's material. We're now going to ruthenium devices. It's also what that gap spacing is. It has to do with balanced topology again. You know, balancing again solves tons of problems here. But that's what we're working on now. Now, the other thing to talk about here, I just made a case for 60 kilohertz, but in truth, yeah, we want to go to higher frequency. And so that's somewhat difficult, because going to higher frequency means losing some sensitivity. And why is that? Because if this is the sensitivity equation, this is the gap spacing between the switch and the electrode, this is the stiffness of the device, and this is what hurts for higher frequency. This goes up. Well, there's frequency right there as well. Quality factor, and a displacement gain just means, I haven't shown this, but you can actually create a mechanical circuit to create displacement gain as well. But you can play around with these factors here, and it turns out that you can reasonably work at frequencies up at 100 megahertz here. Your sensitivity will probably not be minus 100 dBm without some help with some circuits on this. But you can work there, and if we can work just at 1 megahertz, which is the AM frequency, then we don't rely on this gigantic antenna out in Colorado. We can have something in every city that can now transmit something to all sorts of things. And you could put these things, since they don't consume power while listening, in anything. Your book, things on the shelves of stores and that sort. You could see Q in this equation here. The Q of that resonator that I showed, because it was metal, was only 1,000. And that's the problem with metal. And you kind of need metal to make that impact switch. But we've discovered very recently methods to increase the Qs of metal materials. And so this is actually a beam made in ruthenium here, 12.8 microns long, 2 microns wide. And we've increased the Q from 5,000 to 50,000 now. 50,000 is unheard of for a metal on chip. And the way we're doing this is we're actually hitting it with an extremely fast rapid thermal anneal. This is not a rapid thermal anneal like you'll find in this lab eventually that goes up in about a second or so. This is an anneal that happens in milliseconds. And it happens because all we're doing is shoving current through the device. Okay, so as we do that here, we find that we can raise the Qs of these devices. And so now this becomes promising to get decent sensitivities at higher frequencies. This device itself, you can see the frequencies of these devices up to 70 megahertz here. Okay, so this is what's in store now. So this is where I'll close right here. my closing remarks. So RF channel selection that I began with here, where possible, I think can enable many new applications, especially for low power. I think micromechanical technology, like I've shown here, or something similar, will likely play a key enabling role, and an all-mechanical communication receiver front end is possible. This ability to listen without consuming power presents many opportunities. Right? I talked about remote-powered clocks that consume picowatts now instead of the microwatt of your RTCs. 1 joule can last, if you had that kind of power, hundreds of years. Now, the bigger problem with batteries is not, it's the 1 joule will probably go away through other means, not just through this device, right? So batteries discharge. So real problem is how do you keep that charge on a battery? But then these always listening receivers, right? Think of your store shelves here. All these products could have these in them. And you, as a company, can centrally, maybe at Colorado, find all of these devices. No one can hide from you with the 60 kilohertz, right, communications. That'll go through almost anything, except huge mountains and that sort of thing, if you live right behind that mountain. Right? But you can then go in and change the price of all your items on a store shelf, or you can change the firmware and something that requires that sort of thing. It's not something that can transmit, because at this frequency, the transmit antenna is too big. But in terms of receive and listening at all times, that is a technology that could change some things. Okay, so finally, what I want to do is acknowledge what supported a lot of this research. So DARPA funded a lot of this work. I should acknowledge the staff of the Berkeley Marvell Nanofabrication Laboratory, which looks a lot like your new lab here, except with equipment in it. And I guess I will say, you may think your lab is empty right now, but I bet very quickly it's going to be full. That's what happened in Berkeley. It very quickly came to a chance where I can get money for equipment, but they no longer let me put it in the lab because there's no space. That will happen in an unbelievably small amount of time. The students who did this work definitely acknowledge. So Mehmet Akgül did all of that filter work that we looked at. Tristan Rochelo, Thurlin Nang, they did the super regenerative transceiver. They're starting the company to do this. And then the Reso switch receiver, the all-mechanical, that was Ronan Liu, Jalal Nilchi, and Alper Ozgurluk, who actually is still in my group right now. And so with that, thank you very much. Really enjoyed doing this.
Thank you, Claire, for a very interesting talk. And let's open the session for questions, maybe 1 or 2 quick questions from the audience.
When you build these couplers in your array, do you lose any? I mean, that's usually a weak spot in integrated circuits. Do you lose any energy in the coupling with those half wavelength, wavelength couplers?
Yeah, you could if they're not sized exactly correctly. So right, you try to make them half wavelength as much as you can, but you can end up, of course, not being half wavelength. But what we find is we don't lose a lot of energy. So if we have a single resonator that is a Q of 160,000, and this actually is published data, an array of 9 of these things has an eventual Q of 116,000, if I have my number exactly correct. So it's still a very high Q. You're losing a little bit of energy. And you're right. Anytime you put many things together, you'll lose some energy. But we seem to be able to retain enough of it, even with a 9 resonator circuit. And you can see this circuit that I showed here is even more than 9 resonators. And that retained its Q there.
And one other question I was curious about, we can talk later maybe, is on the mass. As you keep making the mass smaller and smaller, does that hurt you in terms of the Brownian noise?
Yeah, so there's all sorts of issues that like I said, I'm not mentioning some of these issues here, but that Brownian noise actually really comes down to just what the equivalent circuit is of the device. So the equivalent circuit is an RLC circuit. The R entirely models that Brownian noise. And if you think about it, F bars have an R of 50 ohms or less. Once these things are 50 ohms or less, that's very little noise, actually, voltage noise. And actually, when you think about it, that's why I like to go around saying our comm systems, they like to use 50 ohms at their inputs, right? That's sort of a common impedance, but we don't need to use that at all. Right? We can use whatever impedance we want as long as the parasitics don't, band limit us or so. So we can go to 1,000 ohms if we wanted to. It actually would be better if we went to 1,000 ohms, because if we had those impedances, then some of the things you talked about, the parasitic interconnect resistances and that sort of thing, would affect us much less. And so this actually is a path to get to higher impedance systems if you could just integrate everything on a chip, which is the goal in the end for a lot of these things. Did I actually answer your question, or did I? There was something, okay, all right.
let's thank the speaker once more.
All right, thanks very much.